Hello everyone, I hope you are doing well. In this video, we'll talk about vectors, its basic concepts, the types of vectors, what are its symbols, representations, formula, and all of the important things about vectors will be discussed in this video. I'll make the chapters in the description box if you're interested in some specific features about vectors. Okay, you can check out the description box for those chapters where you can directly jump into the part you are interested in. So let's start with the definition. What are vectors? So let me tell you first by myself without writing down here. Vectors are the physical quantities. Okay, we know that physical quantities are very important in physics. In physics we define quantities as physical quantities which could be measured, okay, experimentally, and can be assigned a numerical value. All of these quantities that could be measured experimentally or observed and can be calculated and expressed in terms of mathematical numbers are called the physical quantities. Okay, and in physics we have categorized those physical quantities into two categories. One is scalars and the other is vectors. Scalar quantities and vector quantities. What happens in case of scalar quantities is that scalar quantities are those physical quantities which require only magnitude for the complete description. But in vectors are those quantities which require magnitude as well as direction for their complete description. I'll explain you right now. First of all, let me explain what are vectors and why they require magnitude as well as direction, why both of these things are needed to describe vectors completely. So let me just justify it first, and then we'll write it down in in specific form, like I write down the definition that you can use to write in paper or as in the form of notes. Okay, so let's understand what does that definition means actually, because this definition is something that we have read again and again and we are being told about it frequently, but mostly and most probably we don't understand it, like what does that mean actually. Can you explain to other person in simple words that why vectors require magnitude as well as direction, like why direction is also needed to completely describe it? Can you explain it to other person? If you can't, then it means that there is some issue in your understanding, and hopefully that understanding and that gaps in the understanding will be filled after this video. I'm really hopeful, and even if you have any queries and questions at the end of this video, you can ask me in comment section. So let's understand that definition, that why. Okay, so let's say you can imagine a situation, a person, you are sitting right here in your room. Okay, this is you, and someone like your some person comes to you and he asks you that where is AHC mall. Okay, where is AHC mall? This is some random name of a mall that I'm using here. So he asks you what is the location of that mall. Now what if you only tell him the magnitude of distance? Distance, it's used to describe the location of a point. So what if you only tell him that hey person, you have to travel 10 meters of distance to reach AHC mall. Now that person doesn't know in which direction he has to move to reach that AHC mall. He can either travel straight away 10 meters, or like that, or like that, or like that, or like that, starting from starting position. This is the starting point, okay, that we can call as origin. Okay, he can travel in almost infinite ways but 10 meters of distance. Okay, and we in terms of uh, physics words, we say that if you are not telling him the exact direction, and if the person without telling you starts moving 10-meter distance, then he can be anywhere on this circumference of this circle of radius r. which is 10 meter, okay, which is the magnitude of the distance, okay, magnitude of the distance vector. He can be anywhere on this circle, okay, because all of these positions are 10 meters away from the starting point. Now here he needs to know the direction. You have to tell him that where to go with 10 meters of magnitude distance to reach ASC mall. For example, ASC mall is located at this position, okay, it at this point on the circumference of a circle, and you'll tell him that you have to move 5 meters this way, okay, and then 4 meter this way, then 1 meter again this way, or something like that. Here's how the necessity of direction arrives. You have to tell him the directions as well, depending upon the roads that are made in your, nearby areas. Let's say here's the street. This is the pathway that he can possibly take to reach AHC mall. So he'll tell him that go straight and take the first right, and then left, and you'll reach AHC mall and travel a total of 10-meter distance this way. Let's say it's 4-meter distance, it's 2-meter, it's 3-meter distance, and it's 3-meter distance again. So this is how you can tell him to reach AHC mall, by telling the direction as well as the magnitudes. So even the first right and the first left, these are some wedge directions that we give, but they tell us that where to take left. It actually tells us the end point of changing the direction as well. So more specifically, I just wanted to justify you people that why the necessity of direction originates. Location, telling the location of a point or of a person or of object, requires magnitude as well as direction for its complete description. So this is what we call as position vector. Position is a physical quantity that can be measured and can be assigned a numerical value, and has some units as well, like meters and all. So we have this position vector for locating the position of any object, person, or anything else, okay. So position vector is one of the vector. Similarly, we have velocity vector that tells us that how fast the body is moving and in which direction this body is moving as well, okay. And similarly, we have displacement vector. Displacement vector tells us that the distance is being covered, but in which direction as well, like the distance is covered in this direction, or this direction. So both magnitude, how much distance is covered, and in which direction the body is moving, this is explained by the displacement vector. And how much distance is covering per unit time is told by the velocity's magnitude, and in which direction is explained and depicted by the velocity vector, the direction of velocity vector. Similarly, you have acceleration. Acceleration is a vector quantity, and there are many other vectors, like force is a vector quantity, and momentum is a vector quantity. We have numerous physical quantities which are vectors, and we have numerous physical quantities which are scalars as well. For example, mass, okay. If someone asks you what is the mass of this ball, then you'll simply tell him 3 kg, okay. You don't have to, there is no sense of asking about direction when you are talking about mass, okay. Similarly, if we talk about volume, if someone asks you what is the volume of a sphere, you will simply tell him it's 3 meters square or 9 meters square. You will never talk about meter cube, sorry. It's meaningless to ask about direction. Doesn't make sense, there is no need, okay. But here the need originates, okay. Here's how we have justified the need of direction in addition to magnitude for the description of vectors. Okay, so now we have totally understood the thing, and now we can officially write the definition of a vector, and you can even justify to some other person who is not familiar with vectors that why vectors are different from scalars, like how vectors are different from scalars and why they require another thing, another piece of information to completely describe them. Now let's write the definition of a vector, which is simply the one that we have said. If you already know the definition of a vector, please write it in comment section so that I'll be notified that you people already know it and you are curious enough like me to revisit the concepts again and again. Because what I used to believe about energy, for example, 10 years ago, now after 1 year I just revisit my concepts because they always get better depending upon my mental capabilities that has been enhanced throughout the year. So vector is a physical quantity that requires magnitude as well as direction for its complete description. For instance, for example, for instance means for example, velocity, position, displacement, force, torque, etc. These are all physical quantities and vectors. They are all vectors. Now let's see how we represent vectors in graphical form. So representation, keep that in mind, vectors are always straight. Okay, vectors are always represented by straight lines. If we refer to this figure, we have three vectors here. Okay, this is one vector since it's a straight line, this is another vector, a straight line, and this is the third vector. So this whole motion is done through three vectors, or we can simply link the first vector with starting from first vector, which is the tail of the vector, and ending it to the here. Okay, this is the resultant vector, we can say, starting point and the end point, meaning to say that if the motion is happening this way, this motion, you cannot say that this curvy kind of thing is a vector. No, it will never be a vector. Vectors are always represented by a straight line. So starting point and this is the end point, you can either represent it like this is the tail of the vector and this is the head of the vector. A vector has a head and a tail, we'll talk about it. You can see here, this is the tail of the vector where it starts and this is the head of the vector where it ends, and they are connected by a straight line. So this is the end point, this is start point, you can join them like that. This is a vector that we call as resultant vector, or we can have some tiny vectors throughout the path which are straight vectors, because even the curved path has many straight motions. So I hope you are getting it, that only the straight motions are vectors. The curved like motions or the linear combination of very tiny vectors okay, of least magnitude. But it's represented by a straight line. Vector is represented by a straight line with an arrow ahead. Okay, just like that. This is the arrow. It has a tail at starting point and head at the end point or terminal point. The how long this line could be, the length of the line represents the magnitude of the vector. Mostly it is not required for us to take the meter rule. For example, if you know the magnitude of a vector is, let's say, 2 meter or 12 newton, 12 units, so it doesn't require us to take the meter rule and take 12 units and we call it as the true representation. This is not always needed, but in some cases, for example, if we want to show that this vector, this is vector A and this is vector B, it shows that vector B has lesser magnitude than vector A. Okay, this comparative representation is done by showing that this is longer vector and this is shorter vector. Okay, and this is not necessary always to take the meter rule and always draw the exact units. That is not required. But if the comparison is being made between two vectors and we already know that one of the vector is not necessarily equals to the other vector, and if we also know that one vector is greater than the other vector, then make this thing happen. Okay, or use random direction as well, because we don't know the direction. If we know, then we'll show it. There's these things that we have to keep in mind while dealing with the vectors. Okay, you'll know about it later on. The information that you already know about those vectors should be depicted through the vector diagram, and the information that you do not know doesn't necessarily be mentioned. Okay, that could be made arbitrary, or randomized selection could be made for those things which are not confirmed about those vectors. For example, if I know that the vector A is greater than vector B, but I don't know exactly their magnitude and I also don't know their directions, then I can choose any direction, like this is A and this is B. Okay, I have used the random directions. So this is something that I am talking about, like you can take the arbitrary directions and arbitrary magnitudes, but you know that vector A is less than vector B. It is being depicted by this vector diagram. None of other information is known, and that information that is not known is not conveyed as well. Okay, so yes, this is something that I was talking about. Now let's move towards the representation. We saw the graphical representation. It is done by this arrow ahead, and the arrowhead shows the terminal point of the vector and the tail shows the initial point of the vector. Initial means the starting point. And we can also give them some number. For example, let's say the initial point is represented by O and the final point by A. So this is OA vector. Okay, OA, we have written the letter O first since it's initial point, and final point A, and an arrow over it to show that it is representing a vector. Okay, like that. You will always write a vector by some symbol and arrow over that symbol to show that it is a vector. Okay, in books what happens is, in books they use the bold letters. Okay, you can see here the F is bold, which means F is force in a vector. Here R unit vector. So you can see here that B in all these quantities are not being bold. So it means they are the magnitudes only. But here you can see that maybe not properly. You can't see it properly. Here you can see here E is in bold letter, R is in bold letter, all of the vectors are in bold letter, like here in the statements as well. Okay, in books it's easy to use the bold letters, but in written form what we do is to put an arrow over the symbol being used for the vector. For example, if it is a position vector is represented by R with an arrow over it. Okay, sometimes we use these things as well. Okay, so but the standard symbol of position vector is this. Sometimes for ease and graphical representation and to differentiate one position vector to another vector, we use such things as well. So don't be confused. Analytically, a vector is represented by a letter with an arrow over it, like A with the arrow over it, it shows A vector, and its magnitude, since it has a magnitude as well as direction, this is the vector, its magnitude is represented, why I'm saying represented again and again, is represented by like that. Okay, these modes with the vector in it, it shows it is the magnitude of vector A, or by simple A letter which is not bold, which doesn't have arrow over it, it also shows that it is the magnitude of vector A. So both of these representations are correct for the magnitude of A vector. If it is a B vector, then you will replace B here. In place of A, you write B. If it's a B vector or whatever it is, and its direction, how to since we have seen that the magnitude of vector A is represented by this and this letter, then how the direction is represented. So what letters we can use to represent it? For direction representation we use unit vectors. So a unit vector is a vector which has a magnitude of 0 but shows the direction of a vector whose unit vector it is. For example, unit vector of A will be represented by capital A with a hat over it. Unit vector. What is the property of a unit vector? A unit vector has magnitude of 1. It means if you find out the magnitude of A vector, it will be equals to 1. Okay, and has the direction of A vector. We are learning the mathematical and symbolic representation of a vector. Graphical representation has already been learned. We can now know that we can represent a vector by this arrow showing this one point showing the tail or the initial point, and this is the terminal point and it is the end point of the vector by an arrow. This is the graphical representation. Now we need to know the symbolic as well as the mathematical representation of a vector, and for that purpose we learned that we can represent a vector by some symbol, which could be capital alphabets, small alphabets, combination of those symbol with the arrow over it. Its magnitude is represented by this symbol. Okay, mods with a vector and arrow over it. Okay, so this, or simply A, it also shows the magnitude of vector A, and its direction is represented by that symbol A alphabet that is used to represent the vector with a hat over it. Okay, this is a hat symbol and we call it as a unit vector. We'll see its definition later on, but now we need to write the vector in its mathematical form. That's why we need to know about this symbol. This is the unit vector of vector A. Okay, this vector, as I told already, has a magnitude of 1, has the direction of A. We will see the significance of taking its magnitude equal to 1. Mathematically, vectors are written as, we can write vector to be equals to vector A arrow over it equals to its magnitude, since direction is also needed, multiplied by its direction. We are multiplying here the direction with the magnitude, because we know that this directional quantity has a magnitude of 1, and we know that in multiplication that if we multiply any number by 1 it remains unchanged. So multiplying a unit vector with the magnitude of a vector does not change the actual magnitude of the vector. The magnitude always remains unchanged. It only tells us the direction of the vector. When it's being multiplied by the magnitude, it only affects to tilt its direction to a certain point. Okay, without this thing, it's like a circle with center and radius OA, which can point anywhere on the circumference of a circle. But when a unit vector is being multiplied, it tells that where this vector is. For example, it's here, so this is actually the this is actually the A vector. Okay, so that's the role of a unit vector. It tells us the actual direction of the vector, and mathematically we write vector to be equals to like A with a unit vector, like that. Sometimes small alphabets are used as well. There is no problem with using the large alphabets or small alphabets. Okay, capital or small. Okay, that doesn't make any difference. Now let's see how to calculate them. Okay, um, in 3D, in three-dimensional space, we have three components: x component, y component, and z component. So in 3 dimension, a vector will have three components. If it is a vector, then it will have ax component, ay component, and az component. Okay, so a vector can be written equivalently to be equals to ax, which is the magnitude of vector in x direction, multiplied by unit vector I. I is used to represent, is the unit vector of x direction. So this is same as like that, but since there are 3 dimensions, so we have to add the magnitudes and directions of 3 dimensions separately. So for ay, we'll have a with subscript y, which shows the magnitude in y direction, and j hat, then plus a z, which is the magnitude in z direction, k hat. Okay, so we can write a vector to be equals to this. Now how to calculate the magnitude of a vector when we know the three components? So we can calculate it very simply. Taking under root of x component squared plus y component squared plus z component squared. Use bracket or not, it's your choice. For example, if you are given with 2i hat plus 3j hat plus 4k hat, if you want to find out its magnitude, what you have to do is 2 square plus 3 square plus 4 square. You will simply take the squares, you will add them up and take the under root, you will get the magnitude of the vector. Okay, this is the method to calculate the magnitude of a vector. And if it's 2D, then remove az, you're left with ax and ay only. If it's 1D, you are left with ax only. Okay, it's very simple. And how to calculate the unit vector? We can calculate the unit vector, I'm using the small letter now, by dividing the vector by its magnitude. Okay. That's simple to unit vector. Just take magnitude here, you left with a unit vector. How to find out a unit vector? Divide the vector with a, so you'll get unit vector. For example, I have vector axi hat plus ayj hat plus azk hat. You'll divide it by its magnitude, which is ax square plus ay square plus az square. This is the simple formula of finding a unit vector. We'll solve some problem related to vectors as well if you really want to understand how to calculate its magnitude, unit vectors and all that stuff. So we'll do that later on, but for now you just need to know these basic formulas. This is for magnitude, this is for direction, and this is the original vector in 3 dimension, and this is the general representation. As we now know about vectors,